One of the greatest challenges we see facing the energy transition is global heat demand. It's more than half of all the energy we consume on the planet. It's 3 times bigger than power consumption, and 90% of all that energy is being provided by fossil fuels, which means it's 40% of all emissions. So if we don't decarbonize heat, we're never going to get to net zero, let alone carbon zero.
Your trusted source for information on the energy transition. This is the Insider's Guide to Energy podcast. Energy Insiders, this is your host, Chris Sass, reminding you that DistribuTech International is coming up in just a few weeks, February 26th through the 29th in Orlando, Florida. It's a fantastic opportunity to look about transmission and distribution, and Insider's Guide to Energy is an official media partner. What that means to you, that means that we're going to be doing live interviews, we'll be covering stories there, and we can even get you a discount to get in. If you have yet to purchase tickets, use code DTPARTS36, and that will get you 20% off, and we look forward to seeing you in Orlando. Welcome, Insider's Guide to Energy. I'm your host, Chris Sass. With me as co-host, Jeff McAulay. And this week, we're going to talk about getting the most efficiency out of solar. On this show, we spend so much time talking about renewables and solar. Wouldn't it be wonderful if we could take advantage of the 1,000 watts per square meter of energy that are coming to the Earth from the sun? And our guest today, Christoph Williams, is going to walk us through that. Christoph, welcome to the program. Let's start out by telling me, where is this heat that you're talking about and where is it relevant?
That is all heat. So global heat demand, whether that's hot water in buildings, for showers, laundries, or for space heating, your homes or offices, and industrial process heat. So that can be hot water all the way up to high temperature process heat in industry. All of that is 51% of all demand is 212 exajoules of energy. It's vast, and it doesn't get any attention, or it does get some attention. It's getting more now because it's the waking giant of the problem. A lot of focus has been on power decarbonization, but heat decarbonization is kind of the waking giant of the problem.
It seems that in some parts of the world, it is fairly common to use solar thermal for hot water heating. And in some ways, it's so obvious. Like, why not put the thermal source on your roof rather than in your basement powered by fossil fuels? So in Greece, for example, it's fairly common to see solar hot water heaters. Is that the kind of application you mean?
Sort of. You're right. When you stand in the sun on a really cold winter's day, so I'm actually in the UK, which is not the sunniest place in the world, but even on a cold day today, it's about, 5 degrees outside. But if you stand in the sun, you can feel the warmth of that sun. Most of the energy from the sun comes in the form of warmth. So why use fossil fuels? Why use electricity to heat hot water? Just use the warmth of the sun. With Naked Energy, the company that we founded, our focus is actually on the commercial and industrial applications. So traditionally, when people think of solar thermal energy, they do think of a single family home, and they think about those kind of cylinders on the roof. Our technology is a kind of pressurized, engineered system for big heat users. So think of hotels, hospitals, manufacturing industry, so food and beverage industry, for example. They need heat all year round, and we can provide about 40 to 50% of their total heating demand from a rooftop system that's well engineered and designed.
I think a few of our audience members are probably wondering how hot this can get, and I think it's important to highlight a couple things. One, you're not talking about mirrors in the desert pointing the sun at a boiling water tower, right? You're talking about either evacuated tube or flat plate. And so that's one clarification. And then two, that actually even in the UK, cloudy days, cold days, that it can get quite hot. So help us understand the technology you're using, and then how hot can this actually get relative to the ambient environment?
The technology that we've developed is called Virtue, and we adopt a vacuum tube approach. Which in the US actually isn't as common. I think in the US there's more commonly flat panel designs. We like vacuum tubes for the specific reason that we can get elevated temperatures. We can go to higher temperatures, which opens up a bigger demand, a bigger market. And with the two products we have, one does pure heat, The range is called Virtue, the solar collector. The pure heat product can go up to 120 degrees Celsius, so 250 Fahrenheit, and is really aimed at those kind of commercial applications. It's pure hot water. We have a hybrid collector. We call that Virtue PVT. So it does photovoltaic energy and thermal energy at the same time. It can produce hot water up to 70 Celsius and very efficient PV power at the same time. And both those products can be installed separately, or they can be combined because they operate at different temperatures, and they can be combined with PV systems and heat pump systems for a holistic energy system. And they've been certified independently, so these are all independently certified technologies.
There's been some interesting news about what you've been doing in your PVT technology. I think there's been folks like Barclays and some large support behind what you're doing. I guess the one question I have is when you mix technologies, PV technologies really come down in cost because you get the economies of scale and it's very cost effective. If I start trying to do both in one solution, so I start bringing the thermal angle in, can I still use commercial off-the-shelf hardware and software to run this, or does this drive the cost of this technology up, or are you driving the cost down?
That's a really good question. So the key factor here is energy density. And energy density, by that I mean how much energy you can generate for a specific area. So you're absolutely right. PV is like a commodity now. It's very ubiquitous in the market, and the costs have come down dramatically. We actually benefit from that cost reduction. So we incorporate the PV cell that is that commodity into our product. And we've integrated it in a very clever way that you get more for a given area. So instead of generating two separate sources of energy like heat and power from two different collectors, by combining them, we get two forms of energy for the same footprint. And what's really important is that we're focusing on customers that would need, say, a roof that's 3 to 4 times the size they have to generate a meaningful contribution towards their energy bill. Yeah, because most commercial industrial buildings are limited by space. And so by combining the two technologies, it means that you're generating greater yields, because you make an investment on your roof. It's like a 10, 15, 20-year investment. You want to make sure that you're maximizing that net present value of that bit of real estate. So it's vital that you make the right decision, particularly if you're a heat user. If you're a warehouse that only needs electricity, PV is a great technology, PV all day long. But if you need heat, so if you're a hotel, hospital, you need heat from that bit of real estate, putting our technology gives you a greater return on investment because you're saving more energy, but you're also saving more carbon. So our technology can deliver twice the amount of energy savings for the roof space and 4 times the amount of carbon savings for the same roof space compared to a standard conventional PV module. And so customers are really identifying those USPs of energy density versus low cost, a relatively low IRR on a system.
How do you design the trade-off between electricity and thermal? How do you do that design trade-off internally?
So we deliberately set out to go to higher temperatures, as you point out. There are other solutions which stay to low temperatures, which is great for underfloor heating and very low temperature applications, that kind of 25 degrees C that you mentioned. But that's a very small market. That's quite a niche. That's maybe swimming pools or underfloor heatings. So we wanted to go to a higher temperature of 50, 60 degrees Celsius, which means you can do sanitary hot water, process heat, preheating. And very specifically, we use silicon cells that have a very good temperature coefficient. So they will lose efficiency, like most things that get hot. They will lose efficiency as you go to higher temperatures. But you lose well under 0.5% per degree C as you go above 25. So you're still getting really good electrical output and getting that high-grade heat at the higher temperature. In some markets as well, you get PV systems out in the field. Those panels anyway are getting to 40, 50 degrees Celsius in direct sunlight, and all that heat is going to waste. You're not capturing that heat, that heat, and your PV output is limited anyway. So we're just getting more of that pie. We're getting a greater piece of that conversion. The technology can convert typically from the sun. You get 1,000 watts per square of energy per square meter, and our technology, we can capture up to 800 watts of that 1,000 watts from that square meter. So it's really an efficient energy density.
Let's change from the theoretical to what you've done. Can you give us something that your Naked Energy has done recently?
Yeah, great question. So we've now done over 100 projects in 9 different countries. And as I mentioned, we're really focused on commercial, industrial applications. And these range from an installation we're doing at the moment with the Mandarin Oriental Hyde Park Corner. So it's a very high-end hotel that has very high energy demands, particularly heat, and high costs. And the costs themselves at the moment are very volatile. So they want to fix those costs. And that's another important USP of energy density, because if you can fix a greater proportion of your heating bill with on-site renewable heat, then you can predict your energy costs going forward, which is great for a business when your operating margins are quite thin. So Mandarin Oriental, which is a great project for us. We've got a project in Germany now with Hilton, so another hotel. We're doing a project now with IHG in Malta. One sector we've done quite a lot on that have really struggled with energy costs is the leisure industry. So we've done a whole series of sports facilities where, again, a big proportion of their hot water heating demand is for hot water and showers. Quite large systems. Some of these are within the 100 kilowatt, 200 kilowatt size. And universities. We've done quite a few student campus projects whereby we're providing affordable zero carbon heat for the student accommodation. And we've done our very first project in Omaha at Creighton University in the US. So very proud of that one. That's our very first project in the US, and that's with our local partners called ELM companies. And that's been operational now for about 6 months.
You mentioned your partnership. Maybe it'd be worth explaining your strategy for North America and what you're really doing to get into the U.S. market.
Yeah, so I think what's really essential is actually, we're based in the UK and we're a European production right now. And as a clean tech business, we don't want to be shipping product all the way around the world, right? That just doesn't make sense. And so with ELM companies, they've set up a new division called ELM Solar, and they are really dedicated on designing and developing opportunities for Virtue, our technology. And we've got very exciting plans in Texas at their large factory in the Colony in Texas. It's a 250,000 square foot facility. Well, I was there just a few months ago, so it's very exciting. We're going to be setting up production there, so we'll be made in America, and we can really maximize the opportunity with commercial industrial projects in the US. They currently operate in 22 states in the US, and initially the focus is on California, Colorado, Illinois, and New York. So yeah, it's a really exciting time with ELM, and the pipeline's maturing really nicely.
And is your partnership set up in a way that you can take advantage of the IRA and some of the tax incentives in the United States?
Really pleased you mentioned that. So absolutely, what's really nice is, according to our calculations, the commercial customers and industrial customers and communities, they can actually get between 60 to 70% of the total capital capex as kind of rebates and savings. There's some very attractive incentives there from the IRA, from the ITC. There's energy community taxes as well, and we saw a kind of really exciting interactive map the other day where actually different regions, from different communities can access other grants. So we think we don't want to rely on grants, but clearly it helps if there are opportunities there. But absolutely, by having the product made in America, our current plan is that we're going to be licensing the technology to ELM to produce the product there in Texas and distribute it there to other states.
There's plenty of people that probably know how to do PV installs.
Yes.
How hard is it to find the skill set to do this new and emerging technology?
The technology itself is novel in terms of how we've designed the collectors, but in terms of how you integrate it, it's all standard. So the pipes, the inverters, the pump stations, the tank cylinders. So you need people that are probably more adept to heating and ventilation sector, and there's a lot of transferable skills. PV installers obviously would be able to install our technology, but you need to understand mechanical design. You need to be able to look at a building's physics, look at the energy profiles, and size and calculate the system. So you identify a really important point, and that's why our partners in the US, they are very much an engineering-led business. They specialize in microgrids, battery energy storage systems, utility management, and so they really understand the customer's demand profiles and recommend the best solutions, and they do turnkey solutions. So education is a really key thing, and it's something that we keep talking about. Is the skills are there, is educating the supply chain. That's the designers, the developers, the installers on how to install these systems, size them properly so they work well and can deliver the returns and savings that they're promised. So yeah, but typically we'd look at engineers, solar thermal installers, or PV installers, or technicians from the heating and ventilation industries are the most adept.
You mentioned savings, so I have to ask about the financing side. And instead of asking, what does it cost on a dollar per watt basis, because you're probably not going to comp to normal solar numbers, it's going to be more expensive because you're providing more. So, how do you quote cost? Do you do it on a dollar per watt basis? Do you do it on a dollar per square foot? And then what does that payback look like for the customer? Is it financed on a PPA basis or a loan, a lease? And how does that materialize from a customer return perspective?
So you're right. We don't look at kilowatts peak because we're providing heat and power, and in the Virtue Hot product, it's pure thermal. So we look at kilowatt hours. We look at a sort of levelized cost of heat, and it all depends on where the customer is in the world. So how much sunshine do they have? What grade of heat do they have? What unit economics in terms of what's their utility rates? What primary energy are we displacing? Is it gas, electricity, fuel oil? And so we typically would, and our partners would size the system. You'd look at the array and all the balance of plant equipment, which tends to be cylinders, pump stations, inverters, and that total capex of a system, depending on where you are in the world, can range anywhere from a payback from 4 years to 10 years or just over 10 years, and depending on where you are in the world. And that's a really important point that you raise, because we're focused on the commercial industrial sector. To date, we are selling systems as on the capex model, so customers are paying for the equipment up front to save them energy for 20 years, which is quite tough, right? You got to be a really motivated customer that's either got really expensive bills, or you've got really tough or sort of ambitious decarbonization goals, right? So the way that we're looking at it now with some of our partners, and we have a new partnership which has just gone public with a big utility company called E.ON, one of the big energy companies, is looking how we turn the model, which has been very tried and tested with the kind of PV industry and the power industry in terms of doing PPAs, is doing heat and power purchase agreements. So we turn it into the OPEX model, which is great because it means these big industrial and commercial users don't have to write a single check on day one. They get all energy savings and carbon savings from day one, and they get an affordable price which fixes their energy costs. So a lot to benefit.
Now, you talked about the customer base you have today. You talked about the leisure industry, universities. Do you envision the heat being used for industrial process as well? The heats you were talking about were pretty significant or could get pretty warm. So is this part of industry as well, or are they just using it for heating and cooling type heat?
100%, yeah, great question. So absolutely. If you look at industrial applications, you can break them into sort of 3 temperature ranges. There's below 100 degrees Celsius, above 100 degrees Celsius up to about 200, 250, and above 250 to 450. That really high temperature is sort of like concrete smelting. That's really, really high temperature. We're not talking that. And the middle range is very much chemicals industry, very, very high temperature as well. We're talking about nearly a third of all industrial heat is actually below 100 degrees Celsius. So that's, food and beverage industry. They need it for sanitization, bottling, the dairy industry, paper and pulp industry, textiles industry. It's huge. the amount of demand they need below 100 degrees C. And we typically look at two customer sets. There is an industrial or commercial customer that is looking to do the energy transition away. Either they've got gas, they're burning gas and they want to transition and become sustainable. And by deploying our technology, we help them on that transition by halving the amount of gas they use. Or they're a commercial industrial customer that's looking to fully electrify. So going, right, we want to get completely off grid, off gas grid, heating grid. And for them, they're incorporating heat pumps, typically. With them, by combining our solution, we're also making those heat pumps, well, they don't have to be as big because we're producing a lot of energy on site. Okay, it's variable, it's intermittent, it's during the day, but you can store heat, right? It means the heat pump is smaller. It means it will work less, it will last longer, and we're reducing the OPEX of that heat pump. So for those customers, we're also helping them as they go on that electrification journey become more affordable.
Do you have a heat battery as part of your offering?
Every single system that is installed for solar heat, solar thermal, has storage. It's a great question because actually solar thermal is intrinsically a storage technology. In Europe, there are over 10 million solar thermal systems that have an installed storage capacity of 185 gigawatt hours. Now that's 185 gigawatt hours you don't have to generate elsewhere to produce heat because you have to have a cylinder. So every time, and a heat pump, and this is what's really nice because if you want to electrify, you go down the heat pump route, a lot of the balance of equipment, a lot of the stuff that you'd have to do, like a new cylinder and the mechanical stuff, is symbiotic to what you need for a solar heat system. So actually, you can use the same cylinders. And so every solar thermal system, for example, we've done a huge project, and it's a famous building which is about to become public, so I can't name it just yet. I can't do a spoiler, but it's in central London, very, very famous, iconic building, has a 15,000 litre hot water cylinder. And the beauty of heat storage is you can store heat for days. So if you have one really sunny day, you can still be using the heat from that sun 2 to 3 days later. It's a wonderful storage medium. You can even store it for weeks and even months if you store it in the ground and you use ground source heat pumps to extract it. So I'm really pleased you mentioned that topic because for me, it's kind of like one of the major enablers for the energy transition. Everyone's focused on electrify everything. It's like, sure, electrification is definitely going to be a way to go. But the challenge is, where is all electricity going to come from? And the grid itself is way smaller. It's 3 times smaller than the total heat demand we need. I think the International Energy Agency recently said we need 80 million kilometers of cables to be able to help with electrification over the next up to 2040. And so it's that's the entire last 100 years of grid infrastructure we've got to do again in the next 7 years. I mean, it's just not going to happen, right? Because grids are a multi-decadal kind of infrastructure. So so this heat storage that you mentioned is, for us, it's a great way to give flexibility to the grid, and every system that gets deployed, whether it's on a home or a big commercial building, industrial building, is adding storage capacity and flexibility to those buildings.
It's great that you mentioned the complementarity between what you're offering and some of the other electrification of heat. You mentioned heat pumps, and that there's actually a complementarity where you can downsize the heat pump. And you mentioned also the storage capability, which makes me think of who is in charge of managing the dispatch of these different resources, or looking at the load and what's in the bank and which system to use and how to use those together. Who do you envision as doing the operation and optimization of that combined system?
So on a typical design system, I mean, we are doing more designs ourselves because we're the technology owners. We understand our technology really well. But what we're doing right now is we're training specifiers and engineers and kind of building engineers as to how best to optimize the solutions. But it all really depends, again, on the customer. It depends on what their usage pattern is, because there are many different types. And it's one of the big challenges for the energy transition. It's like there are so many different options, right? There's how many different heat pumps are there? There's so many different types, right? And there's new ones coming along. And so which one is right for the particular application? So I think training educating and the specifiers and the designs of these systems is really key. And we're working with some big engineering groups that we are building holistic solutions with, but those do need to be standardized to a limit, because standardization really helps, but you need a lot of flexibility depending on each customer.
As we're going through this conversation, you're covering a lot of ground, both technical, financial, market, and all over the world. Can you tell us a little bit more about your background? How did you get to this point where you've got such a grasp of all of these different facets of the business?
It's a great question. You're not going to quite believe it, really, because I have a very unusual career path to where I am today. Um, I used to be in the advertising industry. So my background is I'm a creative person. I used to work on global TV campaigns, very high end, very technically challenging, very big brands. Um, in that time, for nearly 20 years, whilst I was doing it, I also worked on global climate change campaigns, energy saving campaigns. I've always had an affinity and a desire to do something sustainable, but wasn't quite cutting it for me in the advertising industry, and I was always looking for a new challenge. And I guess that came to me because my grandfather was doing renewables in the 1970s. My grandfather was a very famous scientist that was doing wave power, flywheel technology in the first oil crisis in 1973. So he told me when I was a little boy, fossil fuels will run out. So one day, we've got to find alternatives, and that stuck with me. And Naked Energy was the vehicle that I created with some good engineers to try and make a change. And they opened my eyes to the heat problem. And that was when we decided, let's design something that can actually have a bigger impact and is very scalable. So that's how the transition happened, and it's been a fun journey the last 10 years.
One thing I like to do with our guests is ask a crystal ball question. And the question is, where will this technology be in 12 months from today?
Great question. So we are now in 9 countries, but I think one exciting development, which maybe is more pertinent for your listeners, is we want to do more in the US. And I think we've got some fantastic partners there now who are building a really exciting pipeline of customers. And Creighton was a really good flagship project. I mean, just last week we saw data that it was actually producing 10 times more energy in the PV system for the same area, which is quite nice. And it was like the big freeze in Omaha. I think it was -10, and it was producing 40-degree hot water. So it's lovely. We want to be doing a lot more like that. We hope to be doing many commercial industrial projects in the US, and just to keep scaling.
Well, thank you so much for sharing your journey, Naked Energy story. We've appreciated having you on the show today.
Absolute pleasure being here. Thank you.